Alright, so if you guys remember what we were talking about yesterday, we were talking about acids and bases, and we were talking about neutralization, and we also talked about titrations. So if you guys remember, when we were talking about titrations, we said that the point of a titration was to try to have our acid and a base reaction reach a neutral point, and to do this we use an indicator so that we can see when it has reached a certain pH. And when we're trying to do a neutralization reaction, we usually use phenolphthalein, because if you remember what I was talking about yesterday, it starts to turn a pink color, so it's very obvious when our clear solution starts to turn pink. So in this example, we're going to be talking about an acid mixing with a base, and we are going until we get to a pH of 7-ish, because phenolphthalein really doesn't start to turn pink until closer to 8. But basically, if we do this, we need to know what concentration we're going to have of the acetic acid. So if we read this example problem, it says that we have 20 milliliters of a 0.25 molar sodium hydroxide. We then titrate it with 23.2 milliliters of acetic acid to the phenolphthalein endpoint, which again is approximately a pH of 8. And so it then wants to know what the concentration of the acetic acid is. So our first step in solving these types of problems is to write a balanced equation. So for instance, we are taking sodium hydroxide and we are mixing it with acetic acid. Now, if you remember, acid-base reactions work semi-like double replacement. So what that means is the sodium is going to replace the hydrogen is going to replace the sodium. So our products are going to be HOH, which we know to be water, plus sodium acetate. But whenever we're doing neutralization reactions, I suggest you don't stop here. What you then need to do is you need to figure out, is acetic acid a strong acid? If it's a strong acid, you need to write it as ions. Okay, so sodium acetate is a strong acid, which means we need to write it as ions. So instead of writing it as NaC2H3O, we are going to write it as Na plus C2H3O2. Now, sodium acetate is not on your list of strong acids. Most of them that we're going to be dealing with will be on your list, but for now I'll help guide you if it's one. Another thing is we probably need to rewrite HOH as H2O, water. So this would be the correct reaction for this process. We split it up into ions because it's a strong acid, which if you remember from yesterday, strong acids ionize completely. There's no compound left over, which is why we are writing it like this. So now, before we move on, we need to make sure that our equation is balanced, which it is. Luckily for us, it's a 1-to-1 ratio. So now we get to start the actual math problem. And when I do these types of math problems, I just do stoichiometry, and I always start with my volume. So just like I was talking about yesterday, what I do is I always kind of circle my numbers that go together. So my 20 milliliters goes with my 0.25 molar. That's where I'm going to start, and this is where I'm going to end. So I'm going to start my stoichiometry. I'm going to start with the 20 milliliters, except I'm going to go ahead and write it down in liters because I know molarities in liters and I need my liters to cancel out. So I'm going to write it as 0.02 liters of sodium hydroxide. Now I have to deal with my molarity, so I'm going to put the 0.25 moles of my sodium hydroxide over my 1 liter of sodium hydroxide. We don't want liters of sodium hydroxide, so now we have to convert it to the moles of our acid. So we have to look at our balanced equation. Everything's a 1-to-1 ratio. So I'm going to put 1 mole, and I'm going to abbreviate my acid as HA, just because who wants to write that out every single time? And over 1 mole of sodium hydroxide. And then, of course, we have to factor in that we're dealing with 23.2 milliliters, so I ran out of room, so I have to add this down here. Nothing is going to go on the top. I'm going to convert this to liters. And all of my units cancel out. My liters cancels. My moles of sodium hydroxide cancel out. And now I'm going to be left with moles of my acid over liters, which is going to give me molarity. So if I do 0.02 times 0.25 times 1, and then divide it by 0.023, I get an answer of 0.22 molarity of my acid, which is my acetic acid. So HC2H3O2. So there is my answer. So let's do another problem. All right, so this one says 10 milliliters of a 0.5 molar sodium hydroxide is titrated with 23.2 milliliters of H3PO4, which is phosphoric acid, to the phenolphthalein endpoint. What is the concentration of the phosphoric acid? Okay, so basically I'm going to do the same thing as I'm going to find the things that go together. So these two numbers are going to go together. This is what we are trying to solve for. We want the concentration of phosphoric acid. This is going to be very similar to the one we did last time. So first thing, write a balanced equation. So I'm going to take my sodium hydroxide and it's going to react with my phosphoric acid. So we have to remember that it's kind of like a double replacement. So my sodium is going to replace my hydrogen is going to replace my sodium. So we are going to rewrite it as HOH plus sodium 3-phosphate. Now I had to add the 3 phosphates because phosphate has a -3 charge. So therefore sodium has a +1, so I need 3 sodiums for every phosphate. So is this balanced? No. So now we have to go through and balance it. So if we have 3 sodiums on the right, we need 3 on the left, which then increases my hydroxide. So now I need 3 hydroxides on the right, so I add a 3 right here. So now I have 3 sodiums on the left, 3 sodiums on the left, 3 hydroxides on the left, 3 hydroxides on the right, 3 hydrogens on the left, 3 hydrogens on the left, and then 1 phosphate, 1 phosphate. So everything's balanced. But before we can start the reaction, we also need to figure out, okay, is phosphoric acid a strong acid? Which it is. So instead of writing it as sodium phosphate, we are going to write it as 3 sodiums, and I had to do 3 sodiums because it was Na3 plus phosphate, 3 minus, and we're not going to write it as HOH, we're going to write it as H2O. So here would be our complete equation balance. So now that we have our balanced equation, we are going to do the stoichiometry. What I do is I always start with the volume and the molarity of my whatever's given to me, the 2 that are given to me. I'm going to go ahead and convert the 10 milliliters to liters, so it's going to be 0.01 liters of sodium hydroxide. Now I have to factor in my molarity, so it's going to be 0.5 moles over 1 liter, and this is of my sodium hydroxide. But we don't want sodium hydroxide. We are wanting our acid, which is phosphoric acid, so now we have to do a mole ratio. So there are 3 moles of sodium hydroxide if you look at the equation, and there is 1 mole of phosphoric acid, and I'm going to shorthand this as HA again because who wants to write that? So we're getting there. So far our units are canceling out, but we don't want moles of our acid, we want molarity of our acid. So now, and again I ran out of room, we have to divide this by our liters to figure out what our molarity is, and our liters of our acid is going to be 0.0232 liters. Again, you guys need to get the habit of converting those milliliters to liters in your head. So now all I have to do is the math. So if I take 0.01 times it by 0.5, divide it by 3, and then divide it by 0.0232, I get an answer of 0.072 molar, and then this is of our phosphoric acid, so H3PO4. And we're done. Alright, so let's do one more example. I'm pretty sure this one is asking us to go to a different endpoint. This one says 0.523 grams of an unknown monoprotic acid is titrated to the phenolphthalein endpoint with 22.5 milliliters of a 0.103 molar sodium hydroxide. What is the molar mass of the acid? So this is the same basic type of equation, it's just it doesn't give us the acid and it's asking us to go to molar mass, not molarity. So we're wanting grams per mole, not moles per liter. So first of all, we need to write a balanced equation. So I'm taking my sodium hydroxide and I am mixing it with an acid. We don't know what the acid is, but we do know it has hydrogen in it, so we're going to say HA. Okay, it is going to break apart into H2O plus sodium plus acid. Okay, this is how it's going to break apart. So now we need to kind of start to do the stoichiometry. Well, luckily for us, this is a 1-to-1 ratio, so that's going to make our math nice and easy. And the reason in sodium hydroxide is a strong base, so now we can just start the stoichiometry. So basically, I'm going to start with what I know, the two things that go together. So I'm going to start at this point, and I'm going to try to utilize that to get to my answer. So we need molar mass. Molar mass is grams per mole. So first of all, I have to figure out moles, and then I can utilize the grams. So to figure out moles, I'm going to do 0.2225 liters. Okay, then I have to incorporate the molarity, 0.103 moles of NaOH over 1 liter of NaOH. But I don't want NaOH, I need of my acid. Well, luckily for us, this is a 1-to-1 ratio. So 1 mole of my sodium hydroxide is going to have 1 mole of my acid. Okay, cancel, cancel, this cancels, this cancel. We're left with moles of our acid, which is actually where we want to stop this time around because we want molar mass this time, not concentration. So we need grams per mole. So now that we have moles, I'm going to go ahead and solve for that. So I'm going to get 0.00232 moles of my HA, and we want grams per mole. Well, it gave us grams, so now what I'm going to do is I'm going to take my 0.523 grams, and I'm going to divide it by the answer I just got, 0.232 moles, because that's the unit for molar mass. And I ran out of room, so I'm going to try to write my answer down here. So if I do 0.523 divided by 0.00232, I'm going to get 225.67 ... which we know we can only keep 3 significant figures, so I'm going to round that to be 226 grams per mole of my acid. All right. So here is some ways that we can do a little bit of stoichiometry when we have acid-base reactions. The most important part is to write a balanced equation, start learning how to identify those strong acids. If they're strong acids, they dissociate completely, which means you write them in their ion form on the product side. If they're weak acids, you would write the ions and leave some of it as a compound in the product side. Just make sure that you know where you're starting and know where you're ending, and you're keeping track of all of your units. So I'll see you in class.